Okay, now that you have had an intro to equilibrium and equilibrium constants and what it means, let's take it a couple of steps further here and talking about what if we have certain numbers for our equilibrium constant. So if equilibrium constant is the products over the reactants, if you have a large Kc, your equilibrium is going to lie more towards the product side. Because if you think about the way that a fraction works, if your number in the numerator is big, that means your answer is going to be big. Okay, so if we have more products, our Kc will be larger. Where if we have a small Kc, that means I'm going to have more reactants because that means my denominator is larger, which will give me a smaller Kc. Okay, so the direction in of the chemical, so how do we reach equilibrium? Okay, so equilibrium can be reached from either side. I can either reach it from reactants to products or products to reactants. It doesn't matter. However, if the reaction is flipped, Kc must be inversed. Okay, so let's look at an example here. Okay, so for example, if I have N2O4 in equilibrium with 2NO2, you have to remember that the coefficient is your exponent for that value. Okay, so my Kc for this equation is going to look like this, and my Kc is 0.212 for this forward reaction, which means I probably have more reactants than products because my Kc is small. Where for this reaction, the flipped reaction, the Kc is going to be N2O4 over NO2 squared, which means I then have to inverse the Kc, which will be 1 over 0.212. Okay? Now, what if we have multiple equations adding up to an overall reaction? Okay? So if moles in an equilibrium are doubled, Kc will be doubled as well. So let's use Hess's law as an example here. Okay, so let's say that I have this equation, 2NO-Br in equilibrium with 2NO-Br squared, and I have a Kc there. And then I have this equation, which is the Kc is 7.2. Okay, the sum of the reaction is going to be the two of the reactions added together. And just like in our kinetics problems, if something is repeated on the reactants and products side, it's going to cancel. And we'll talk about why that here is in a second. So Br2 is going to be canceled here. So what that means is if I multiply their Kc's together, so this is the Kc for the top reaction, this is the Kc for the bottom reaction, you'll notice that Br2 is in the numerator, where Br2 is in the denominator for the second reaction. So if I have a top and a bottom, they cancel each other and just becomes 1, which means in order to get the overall Kc for both of the reactions together, we multiply them. So I would do 0.014 times 7.12, and so the equilibrium constant for the overall reaction for these two guys is going to be 0.10. Okay, let's look at another example here. Okay, so let's say we're given this reaction, and sorry I've already written over this, but you guys can follow along. If you're given HF and you're making H plus and F minus, and then you're given your second equation written here, okay, and then it tells you that this is the overall reaction, how are you to find the Kc for the reaction? Okay, well there's a couple of different things that you have to do. So you'll notice, if you come down to this equation, you'll notice that you start with 2 HFs, where your equation only gives you 1. So what you have to do is you have to multiply all of your moles, and anytime you multiply your equation, instead of multiplying your Kc, you have to take it to the power in which you're multiplying the moles by. So I would do 6.8 times 10 to the negative 4th squared, which gives me a 4.624 times 10 to the negative 7th. Okay? And then you'll notice down here as well that your H2C2O4 ends up on the product side, where it's on the reactant side here. So since you're flipping the equation, you have to take the inverse Kc for that reaction. And if I do that, 1 over this value, you get somewhere close to 263,150, and this should be 8 because I forgot to round. And then after you do that, since now you have your overall reaction and you adjusted your Kc according to what the overall reaction is, you can just multiply your two Kc's together to get the Kc for the overall reaction, So the Kc for this overall reaction should be 0.121. So to summarize how you do these, if it's a reverse direction, you take the inverse. If it's multiplied by a number, you take the power. And if it's 2 or more steps, it's going to be the product, which is mean multiplication of the equilibrium constant for each individual steps. Okay? So we'll work on these problems in class, but if you want to get a head start, that's good practice for what I just talked about. Okay, the next thing I want to talk about is heterogeneous equilibria. There's just 2 definitions that I need you to know from this section, and that's if you have a homogeneous equilibrium, that means that the substances are all in the same matter, so that means gas, 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 aqueous, aqueous, aqueous. Where if you have heterogeneous, that means you have multiple states of matter in the reaction. So that would be like aqueous, aqueous, liquid, gas, gas, liquid, okay, anything like that. And then section 15.5 is how we calculate equilibrium constants. So this is where our Rice table is going to come into play that I kind of discussed on the first page of your note packet. Okay, so this example is actually on page 643, so if you want to follow along in your book, you're more than welcome to do so. Otherwise, you can just follow along with me. So, we're given an equation. We're given H plus H2 plus I2, and we're making 2HI, okay? So, we have to remember that our Rice table is going to help us solve for what we have at equilibrium for everything in this equation. Because ultimately, you have to remember, for K, we need to have everybody's concentration at equilibrium in order to solve for Kc. So for example, ultimately, what I'm trying to solve for, if Kc for this reaction is equal to Hi squared over H2 times I2, I'm given Hi at equilibrium. What I'm not given at equilibrium is H2 and I2. So that is what the Rice table is going to come into play for, because it's going to help us solve for H2 and I2 at equilibrium. Okay, so your Rice table, reaction, initial, change, and then what we have at equilibrium. Okay, so our givens. Initially we are given H2 is 1.000 times 10 to the negative third concentration, okay? Initially, we are given 2.000 times 10 to the negative third of I2. And since this is initially, the reaction hasn't even started yet, which means we have 0 molar of HI. Okay, now, here's the next thing. We also have the at equilibrium for HI. So that is going to be 1.87 times 10 to the negative third molar, which is what we're going to plug in for our HI here. Okay, so ultimately, if I know that I have this amount of this product at equilibrium, I know that I have to go from 0 to 1.87 times 10 to the negative third molar, okay? Now, since we're saying molarity, we're going to assume 1 liter. What we can do now then is use stoichiometry and use our equation to help us, and I'm sorry I didn't put my 2 here, which that's really important because we're going to use stoichiometry to go from what we're given to see how much of H2 and I2 we needed in order to solve for this. So ultimately, what we're going to say is question mark moles per liter, or molarity, but since this is just 1, it doesn't really matter. Okay, and we're looking of H2, and if we're given 1.87 times 10 to the negative third HI, I have to figure out how many moles of that H2 I needed to make this amount of moles of HI, okay? So ultimately, you're just using your chemical equation to do that. So for every 2 moles of HI, I only needed 1 mole of H2, which means you're only getting half of the amount from your H2. So with that being said, if I start with 1.00 and I do this math, so if I say 1.87 to the negative third divided by 2, that means that I used 9.35 times 10 to the negative fourth H2 to make this amount of HI. So with that being said, my change is I'm going to subtract the 9.35 times 10 to the negative 4 because that's the change. That's not what I have at equilibrium. What I have at equilibrium is this 1.00 times 10 to the negative third minus the 9.35 times 10 to the negative fourth. So if I do that math, what I have at equilibrium is, 6.5 times 10 to the negative fifth. Okay, and that makes sense because I'm losing H2 to make HI. So then for I2, I'm going to do the same thing, but what we're slowly going to realize is that it's going to be the same amount because the mole ratio is the same. But just for practice purposes, let's just do it. Okay? So for every 1 mole of I2, I will make 2 moles of HI, which means I am also losing 9.35 times 10 to the negative fourth. Okay? And I'm going to do the same thing. I'm going to do 2 times 10 to the negative third minus the 9.35 to the negative fourth, and I end up with 0.001065 at equilibrium. So now that I have all of the values of each substance for this chemical equation at equilibrium, I can plug it into Kc and solve for the equilibrium constant. So what I would do is I will say 1.87 times 10 to the negative third squared divided by 6.5 times 10 to the negative fifth times 0.001065. And then I plug that into my calculator. And I end up with my Kc for this reaction. And since I'm given 3 sig figs here, I should have 3 sig figs in my Kc. I end up with a Kc, or an equilibrium constant, of 50.5. Okay? We'll do more practice like this in class, but that kind of gives you a head start in understanding equilibrium constants. Thanks.